Hi everyone, it's Saturday morning, so I'm looking a little tired still. Had a big middle school dance last night, so I'm all partied out from all the middle school dancing. Uh, anyway, I wanted to go through the lesson that we had yesterday on universal gravitation and just give you, again, I've uploaded these slides, but I just want to give you another video here to kind of walk you through some of my thoughts on each of these slides. But again, all this pertinent information is available in Classroom on PowerPoint, as well as this video that I will attach to that same post. So here we go. We're going to be using mathematical representations of Newton's law of universal gravitation to describe and predict the gravitational forces between objects. So I have my phone, and I have this wallet, and they have a gravitational attraction between them that's dependent on a couple of things, which we're going to discuss briefly. Number two, explain that forces at a distance, so a force is a push or a pull at a distance, are explained by gravitational fields permeating or going through or existing within all things. So permeating space that can transfer energy through space. So it kind of sounds like Star Wars with the force, right? Gravitational field, and there's a force that permeates space that can transfer energy through space. Now, this concept of universal gravitation that permeated all space sort of freaked out Isaac Newton, and it even freaked out people like Einstein, who was working on gravitation and figuring out that spooky action at a distance, as Newton called it, when Einstein came up with his laws or his views on what we now know as relativity, so special and general relativity. And that was trying to solve this puzzle of spooky action at a distance. Because if Newton was correct with his law of gravitation, that meant that something very far away could affect something very far away, but there was no physical medium or field for them to interact within. So that was a puzzling thing, as you might imagine, in the 1600s and into the early 1900s. And it wasn't until Einstein that we got a lot of that fixed up. And now we're still working on gravity, and we're working on quantum gravity and gravitational mechanics. We just discovered the first gravity waves in the universe, and that Nobel Prize was awarded for that because of the LIGO system that we're going to talk about on Monday. Very, very cool stuff. So we're building on the shoulders of Newton, Einstein, and the folks that we're going to talk about on Monday, who are still doing cutting edge work on gravity, because we don't really understand how this thing works. But we've got some good math behind it, and that's what this is about. And that's what physics is about, is taking representations of the universe as we understand it and continually improving on that using data and observation, and we need your help. So we do know about free fall, and it's kind of a cool thing because space and astronauts, and we all want to be astronauts and space people when we're young and old. I would love to go to space. So what causes free fall? We talk about free fall a great deal, but free fall exists here on Earth as well, so I can drop my phone. Please don't do that. Yay, Apple Care. But if I were to do that, it would be in free fall for a second. Maybe. Let's talk about that. Gravity is a non-contact, so there's no contact for gravity to exist. Some forces need a contact, like, again, phone and wallet. That would be a contact force, pushing and pulling. But gravity is a non-contact force. It still does the same thing. It just doesn't require physical contact. That is attractive between any two objects having mass. So what that tells us is that any two objects in the universe that have mass, which is most every object that is an object, has a gravitational attraction to every other object. It's kind of cool. Gravity is the non-contact attractive interaction between any two objects having mass. I really like this definition. And what this tells us is that weight, which is the measure of the pull of gravity here on Earth, or on the moon, or on Jupiter, which can't really stand on Jupiter, or on Venus, for instance. But weight is a measure of the pull of gravity, that non-contact attractive force. Weight is inversely, so upside down. One goes up, one goes down. Inversely proportional, another big word, proportional, to the square of the distance between the centers of mass of the object and of Earth, or Venus, or Mars, or whatever large body you're being attracted to. So it's inversely proportional to the square of the distance between the centers of mass. So if you play football, or if you play baseball like I did, if you play golf, oh, my button's a button. Oh, no, it's not. Yeah, it is. I like having this button. If you play a sport like that, your center of mass is very important. If you're a cheerleader, if you do track and field or cross country, your center of mass is very important, and knowing where that center of mass is. And we did some stuff earlier this semester where we were trying to push against the wall. We had our head against the wall, trying to pick up a chair. And if you're, biologically one way, it's a little more difficult to do it than another way because of your center of mass and basically the way that the gravity of Earth pulls down on you. And it's inversely proportional to the square of the distance between the centers of mass. Sounds complicated, it's really not. So this is Earth, obviously, and here we're just representing the center of the Earth, and this is one radius. So we're not going all the way through the Earth. It's not the diameter of the Earth. It's not the circumference of the Earth. We're not going around. We're going from the center of the Earth out to the surface. That's one radius. So if we double that, we have 2. So 2 radiuses sub E, so 2 radiuses of Earth, 3 radius sub E, 4 radius, 5 radius of Earth, 6 radius, right? If you have a 1 kilogram object, it is about 9.8 newtons. Because in physics, we like to measure things in newtons when we're dealing with weight, and we'll see why. It makes everything much cleaner instead of pounds or kilograms. So we have our 1 kilogram object, which is about 9.8 newtons, and that has about 9.8 newtons at 1 radius of Earth. So 1 kilogram object. Now, if we were to go to 2 radiuses of Earth, so take your radius of Earth, double it, that object would have a much smaller weight in newtons. And then if you go to 3 radiuses, it's going to have even smaller. So we've got about 1.68, I believe, newtons at 3 radius, 4 radius, even smaller. And you see we start leveling out because it's an inverse square. We'll talk about that. So here's Newton's big reveal. Gravitational force, again, is proportional. So it's in relationship. It's proportional to the product, multiplying, of the masses. So gravitational force, represented by F here, is proportional. So that helps us explain this. I can't get my cursor to do that thing again. Explain this division line here. Proportional to the product of the masses, so M1, M2, mass 1, mass 2, involved in the system here. And inversely proportional, so this is going to be on the bottom because it's inversely proportional, to the square of the distance between them. So R sub 12 squared. So radius 12 squared, distance between the centers of mass 1 and mass 2. Now, what's nice is that it's pretty easy to plug these in. So to find the gravitational force and this proportional example here, it's pretty easy because, not pretty easy, but it's made easier, I should say, because you have the gravitational constant, which is super tiny, 6.674 times 10 to the negative 11th. So you've got a 1 with a lot of zeros behind it. We're going to do some examples of this tomorrow. And then you've got your unit, which is a cubic meter over kilogram times second squared. Now, the nice thing is, at the end of this, we're going to find out when this all simplifies down, you're left with the same unit as you have for acceleration, because gravity uses the same unit as acceleration, meters per second squared, or kilometers per second squared, but generally meters per second squared, which is kind of fun. And if you think about it, it makes sense because everything falls here on Earth at 9.87 meters per second squared. And the way we know that is because we plug any mass into this formula and we multiply it with the gravitational constant. We take the inverse square of the distance from the surface of the Earth to the center, the radius of Earth there, and everything's going to always equal the same. There's no way not to equal the same. So that's why I always, have the example of that heavy lead ball and like my phone. And if we drop them, they hit the ground at the same time. Lead ball does damage to the floor does damage to my phone. That's for some other principles. But it's kind of cool if you think about it. So you plug any masses into this formula because the gravitational constant here is so small, it's so tiny, you're going to get the same thing, basically. So everything on Earth, not counting air resistance, falls at the same rate. And we showed this, as we're going to look at on Monday, when we got to the moon. And we had an astronaut drop a hammer and a feather on the surface of the moon because there's much less air resistance because there's a little atmosphere. There's a tiny, tiny, tiny little bit, but nothing recordable. and the hammer and the feather fall at the same time to the surface of the moon. Kind of cool. All because of Newton in the 1660s. Well, not because of Newton, but all because Newton helped us realize this formula in the 1600s. Amazing. So let's look at this last mathematical construct here. And this is a pretty easy representation. We spent some time on this yesterday, but I really want you to be able to see this and not be afraid of it and label it and own it and understand it, because it's super important. So we have two objects. We have M1 and M2. So we have our apple, and let's say we have an orange over here. They are gravitationally attracted to each other. And they have a radius of distance between each other. So from the center of the object out, right? So if we double the mass of the apple, I believe, whatever the object of M2, if we double the mass, keep the radius the same, the force of attraction doubles because it's proportional. On the other side, the same thing happens, which is kind of cool. So the force of attraction for M1, the smaller object, which doesn't change mass, it has twice the force of attraction to that larger object. So the larger object has more force of attraction. The smaller object doesn't change mass, but it also has double the force because it's all proportional according to this. M1, M2, that force is proportional. So if the mass of one of the objects doubles, then the magnitude of the force on both objects double. And remember, magnitude is just a fancy word that we use in physics for strength or amount or the load in a system, if you will, but magnitude. Okay, so let's take our same object here. We have one object, another object. These are the same size. They have a mutual attraction force. We have our distance represented by R, by the radius between these two objects. And we're going to double that distance between the two objects. So if this is the Earth and the Moon, we're going to double the distance between the two objects. And if the distance, represented by R, doubles, the resulting force is a quarter or 1/4 of the original because it's an inverse square. So here it doubles. And here, because we changed not the mass, remember, mass, but in the second one, we're going to change the distance, R. If we double the distance, the resulting force is 1/4 or 1/4 of the original on both sides because we've changed the distance. Now, if we were to go back and change the mass on M2 over here, that would double the force, but it would not account for the distance. And we can look at that, and we're going to do some interactive slider type stuff. This helps us explain so many things in physics and nature, and it's pretty interesting. And then we wrapped up by saying that a gravitational field, so gravity operates in a field. Gravitational field is a vector field having two components, having speed in a given direction type thing. A vector field in which the physical quantity is the gravitational force per unit mass. So what that says is, like we looked at NASA's GRACE mission, which had two satellites together in a joint orbit, but we had to make sure they didn't collide, and we had to make sure they stayed in orbit at the right size, so we have a distance between them. And we have this mg left and mg right. So this is the physical quantity of the gravitational unit per mass. So the mass of this object and the mass of this object are affected. And then you have the mass of the Earth, of course, down here. And we talked about how gravity on Earth is not smooth and even, which the GRACE mission helped us realize. And because of that, we're able to map out this gravitational field and how it sort of warps and bends because of the way that the core of the Earth is spinning. So the gravity in some areas of the Earth is a little tiny bit less equal to other parts. Down here in South America, you see a big spike. We've got a big spike here along what's south of Greenland down into maybe the Azores off the coast of Europe. Up here in Alaska, we have a big spike. There's a huge spike over here near Australia. So kind of cool stuff. And then we talked about field lines within our gravitational field. And we represent gravitational fields, or any field, using field lines. So this can be a magnetic field, which we're going to study in the spring. But for gravitational fields, we represent the fields using these field lines. So this is the Earth-Moon system. And you see these field lines have arrows on the Earth that all point down, because remember, this should be kind of thought of in a 3D situation where you have like that heavy lead ball that's impacting that towel that we use, and it bends space and time. Earth does, because of its mass. So things are literally falling into Earth. So Earth creates a dent in space and time. And the Moon does as well, but it's not as severe. So therefore, the gravitational field lines here are warped by the gravitational field of the Earth. And there's a cool point called the neutral point, which we discussed. We had a great question about between the Earth and the Moon, where there's neither a push or pull from the that's overwhelming from the Moon or the Earth. So we call it a neutral point. We did a lot of math on this in the 1960s when we were trying to get to the Moon in the Gemini and then the Apollo programs. And we have some very famous scientists to talk about on early next week. Asked you to read up on one on Thursday night. So make sure you've read up on that. We're going to talk about her in the coming week. And she helped us realize some of this incredible science. And then last but not least, I think this is such a cool illustration and something to think about, because we are so close to the surface of the Earth. We think of gravity linearly, right, like in straight lines. But this is a vector field. So these fields are perpendicular in some ways, but then we start getting these bends because the Moon affects the Earth's gravitational field. And vector fields with evenly spaced field lines and constant magnitude throughout space are called uniform fields. So here on the surface, we kind of see this uniform field. Or if we're close to the Earth, not where the Moon is affecting the gravity of the Earth, those field lines are also evenly spaced. But as we're going to see, gravity is not always a uniform field. And that is where the math gets really fun. But for uniform fields close to the Earth, definitely here on the surface of the Earth, or if you're on the surface of another huge planet, even the Moon, satellite, then the gravity field lines will be expressed as uniform field lines. But again, not always the case. So we're going to talk about that in the coming week as we sort of expand our knowledge of gravity. So that's the big chunk of it there. I know this formula looks a little daunting, but it's once you kind of get into it and start playing with it, it's not so rough. Just know that universal constant, the gravitational constant, is going to help you and be your friend. And just knowing the mass of two objects, as well as the distance between them, between the centers of mass, is going to help you. So we're going to do some fun calculations next week about your attraction to the Earth, your attraction to some other objects, and we're going to look at how and why the Earth kind of destroys that chance for you to be gravitationally attracted to a piece of paper or something like that. In the meantime, thank you for coming to Thomas Sumter, and I hope you have a great weekend. If you're watching this early next week, I hope you have a great week. If you're watching this in prep for the exam or the end of the semester or next semester and you want to get some review as we get into electromagnetism, I hope you have a great day, and we'll see you soon.